Okay, can everyone see that okay?
Yes.
Yeah. Okay, excellent. All right, well, yeah, thank you again so much. Thank you for the opportunity to speak with you today. As we were saying a bit before, it's exciting to have the opportunity to give talks, across continents. So I appreciate the opportunity. So I want to first acknowledge, I'm going to be talking about results from a lot of collaborations and different teams. And so I want to take a quick shout out to them here. I'm going to talk about kind of 3 distinct projects that have a variety of international collaborations and facilities. Okay, so I want to start by talking a little bit about sort of our place in the local cosmos. And so if you were to go out on a very dark, clear night from a dark sky site and look up at the sky with your naked eye, your view might look something like this. So we know our visual magnitude to the naked eye is about 6 magnitudes from a really dark site. And maybe the night sky would appear to look like this to your naked eye. But if we had the same sensitivity to the infrared at maybe say 2 microns, our night sky would look dramatically different. This is something that we've learned in part due to surveys like the 2-mass infrared survey, which has shown us that the preponderance of nearby stars are not in fact, more massive bluer stars or sun-like stars, but are in fact very cool, dim red stars known as M-dwarfs. So to give us a little bit of context for what I'll be talking about today, we'll go back to the canonical HR diagram showing the visual magnitude on the y-axis and the V minus R color on the left. And as you can see throughout the main sequence, eventually you get down to a temperature regime around 3000 Kelvin where you get into the M-dwarf regime. And if you go to even lower masses, you start to turn off a little bit here at the reddest colors and no longer stably fuse hydrogen and enter a regime we know as the brown dwarfs, which are about less than 8% of the sun's mass. So M-dwarfs, as sort of visualized in the cartoon that we just saw, are over 75% of stars by number in the Milky Way. And that means they make up over 50% of the stellar mass content of our galaxy. They actually span a pretty wide range of masses when you consider spectral types. So the lowest mass M star that can stably burn hydrogen is about 8% of the sun's mass, but the most massive one in the spectral class is 60%. And they span a pretty significant range of luminosity as well, from 0.01% to 6% of the sun's luminosity. As we go down to even cooler objects where you no longer stably fuse hydrogen, you enter the brown dwarf regime. So shown here on the left is another sort of HR diagram or color magnitude diagram, now in infrared color, looking at J versus J minus K or J minus H. And you can see the sort of tail end of the M-dwarf sequence up here at the top. But then as you cool down, you actually see this very interesting sort of turn as you go from what we know as L-dwarfs down into T-dwarfs. So to give some sort of context for this, if you look at the sun, a G main sequence star, and you look at a typical M-dwarf, which might be about 3600 Kelvin, eventually as you cease to burn hydrogen, you enter this regime where all of the objects are electron degenerate. So these L, T, and Y type objects are actually all about the same radius as Jupiter. They exist in this very interesting sort of intermediate space between stars and planets where they can't fuse hydrogen. Some of the more massive ones are able to burn deuterium, but they're quite a bit larger than Jupiter, tons of times of Jupiter's mass. As we go into these spectral classifications, the first ones were discovered in 1995, and the most recent discovery, the most recent addition to our main sequence of sorts are the Y-dwarfs that were discovered in 2011. And the main difference between these different classifications are really related to temperature, and that's what we're seeing in this physical manifestation in the HR diagram. So the L-dwarf regime are sort of the hottest brown dwarfs. They're on the order of 2500, 1500 Kelvin, and their atmospheres are hot enough still that you are able to get metallic species like titanium oxide, vanadium oxide, various hydride species in the atmospheres of these objects. And they're cool enough that those metallic vapors are able to condense occasionally into dust particles. As you cool down even further from about 900 Kelvin to 1500 Kelvin, those particulates actually, the chemistry starts to change and you're able to take what was originally carbon monoxide gas and take that carbon and form it into more complex molecules like CH4, methane. You start to see water molecules, H2 molecules, and we think that the actual dusty cloud decks in these objects sink to lower layers in the atmosphere, and I'm going to talk a little bit about what that looks like later. Then as you cool off even more, you get into what we call the Y-dwarf regime. This is, very cold, 300 to 500 Kelvin. And now you're starting to see more and more complex molecules, even things like ammonia, which are signatures that we know well from Jupiter's atmosphere. And again, these mass ranges are sort of from a few times the mass of Jupiter all the way up to 80 Jupiter masses, which is about where the onset of hydrogen fusion kicks on. So I'm going to briefly talk about exoplanet detection methods, because we're talking about this regime that's sort of stars all the way down to planets, which many of you are likely already familiar with. But of course, we have the radial velocity variation that is used to detect the first exoplanet in 1995, and we've had remarkable success with looking at the Doppler shift due to the planet orbiting. The transit method, which was first discovered in 1999 of planets eclipsing the host star. And then the one that I'll focus on today is direct imaging, which has not yielded the most planets, but gives you a very sort of unique method to probe the luminosity of the planet directly. As you can see in this video, of images that were taken over the course of about 10 years from the Keck Observatory of the HRA 799 system. So these are 4 gas giant planets at tens of AU from their host star, which has been blocked in the center of this image. And you can actually see the orbital motion of these planets through direct imaging. I really like this movie of exoplanet detection. So we're looking at mass on Earth masses in the y-axis, and then the period of the orbiting planet in years. And this just goes to show our solar system. There's a bit of a dearth. Suddenly we start to detect exoplanets using the radial velocity technique. We're really sensitive to massive planets at sort of short periods. And then the red dots you can see are the transit method, so looking for those eclipses, which has some remarkable success in the sort of late 2010s with NASA's Kepler mission, which has really discovered the bulk of the exoplanet. The 4,000 exoplanets that we know of today have been in large part discovered through transits from Kepler. But I show this to kind of motivate the fact that Kepler has run out of fuel, unfortunately, and the mission has ended. But NASA's Transiting Exoplanet Survey satellite, launched in 2018, is using the same technique to look for these eclipses of planets, but is actually really focused on these extremely abundant M-dwarf stars. And so TESS has already found a few tons of planets. It's going to yield, possibly hundreds in the next couple of years. And its focus is really on the closest stars, the majority of which are cool, dim, red M-dwarfs. So understanding their properties is really quite timely as we start to fill in this parameter space. Okay, so I'm going to talk a little bit about the motivations for why we should care about the lowest mass stars, these M-dwarfs, as exoplanet hosts. And then later on, I'll talk a little bit about why we should care about brown dwarfs as exoplanet analogs. So as I mentioned, low mass stars are abundant. They outnumber higher mass stars by a factor of 3 times. They're long-lived, and so because they burn hydrogen so frugally, their main sequence lifetimes are on the order of trillions of years. So we've never actually seen an M-dwarf evolve off the main sequence or die. That might be good for habitability, potentially, if you care about long-term stability of your stellar planetary system. The fact that these red, small, dim M-dwarfs are small and low luminosity actually makes detecting their planets quite a bit easier. And so that's sort of ripe territory to understand, the smallest planets are easier to detect around smaller stars. And then there's this sort of outstanding question that people argue about a lot, and we haven't really come to consensus of whether or not M-dwarfs are actually good environments to host planets. And this sort of comes back to this habitable zone argument, where we know that the liquid water habitable zone around a hotter star is correspondingly further away from the star, but for cool red M-dwarfs, the habitable zone is likely to be much, much closer to the star, potentially even in a regime where a planet might be tidally locked. And so there's a lot of other complex considerations to include there. A really noteworthy recent example is the TRAPPIST-1 system, which was discovered in 2016. So this is had sort of a splashy cover of Nature, where the host star is actually right at the stellar brown dwarf boundary. So it's actually only 89 Jupiter masses, really in this regime of whether or not you consider it a star or a brown dwarf. But it had multiple planets, and one of the things we'd like to understand are these kinds of systems common? If we know that these kinds of stars are the most abundant stars in the galaxy, is this the predominant route by which planetary systems form in the Milky Way? And just to give you a sense of scale, the TRAPPIST-1 system, you could pack all 7 of these planets, which span the liquid water habitable zone, well inside the orbit of Mercury in our solar system. So this is everything scaled much, much further down with a whole ensemble of planets that are roughly Earth-sized. Okay, so I'm going to tackle 3 sort of main motivating questions in this talk relating to star and planet formation around these types of objects. First, I'm going to talk about how often we find low-mass stars in binary or multiple systems, because that informs our understanding of how their planetary systems might evolve. I'm then going to talk about much younger, more distant systems and try to understand how much planet-forming material exists around the youngest, lowest mass stars and brown dwarfs. And then I'm going to close out the talk by talking about just one single brown dwarf and how it can be a useful sort of laboratory for understanding exoplanet atmospheres. So I want to start by talking about binary systems. And so binaries give us a really good insight in terms of the star formation process, understanding things like the initial mass function, but also the interplay between planetary systems and their host stars. So one of the ways there are many ways we can detect binary systems. I focus predominantly on trying to use direct imaging, which is either using adaptive optics imaging or traditional direct imaging. And what you'd really like to do is combine as many of these techniques as possible to basically understand, if you're going to do a large survey of binaries, how often do you really find stars in binary systems? And you can see this example. I like this sort of general cartoon of how adaptive optics systems work, but essentially you have the light incoming from the telescope, which is distorted through the Earth's atmosphere. You then run a deformable mirror about 1,000 times a second to undo the effects of the atmospheric turbulence or blurring, and you end up with a much sharper corrected image. And you can see the sort of dramatic effect of that in terms of binary studies down here on the left, where if your adaptive optics system is off, you may be 2 blobs, you could argue. You turn it on and your image resolution increases significantly, and you can see that this is actually an unresolved pair, and there's actually a much fainter companion that would have been totally invisible without AO. Oops. So I am going to talk a little bit about what we know already about stellar multiplicity and this sort of broader context for binary systems. So in terms of understanding how often stars are found in binaries, this has always been a motivating question to understand the sun for context, like is the sun unusual or typical in being a single star? And so a lot of emphasis has been placed on solar type FGK stars to understand their binary fractions, more recently for A-type stars, so more massive stars. And then a lot of the M-dwarf surveys were significantly older. And part of this challenge is that M-dwarfs have been surveyed in sort of an inhomogeneous way or with a very specific or biased set of techniques, and they're just faint and challenging to observe. So really the motivation for this is trying to understand how do we put together a well-defined sample to measure binary statistics. And the reason we'd like this, of course, is we'd like to see binaries as this dynamical imprint on how star formation occurs. We'd love to be able to compare the statistics of our nearest neighbor stars to those of younger star-forming regions and understand how universal the IMF is. We'd also like to have a sort of uniform separation in mass range to find binaries and be able to do that really to understand the effect of binaries and stellar companions on forming disks and planetary systems. And this has a lot of really important implications for all of the planets that we'll probably discover with the TESS survey. So I'm going to talk briefly about the M-dwarfs and multiple survey, or M&M survey. This was a effort to characterize a well-defined sample of the nearest M-dwarfs. And so on the right here, what we're seeing is a visualization from Adric-Rudel of our stellar neighborhood. So this is at the sun at the very center of this image, and these are all of the stars that are within 25 parsecs of the sun. You can see that the overwhelming predominance of them are M-dwarfs, and I'm focusing just on the closest 15 parsecs so that we can try to measure their companions with orbital separations from 1 AU all the way out to 10,000 AU. The way that I've done this in particular is to focus on imaging methods. And one of the benefits of looking at the nearest stars is that it's actually quite straightforward to detect physically bound companions that are co-moving in space with their host stars. So here's an example of what an adaptive optics image looks like. This gives us really high resolution to search for close binaries. As you can see in this image, the separation is only about 1 AU from the primary star and its companion. And so this was a combination of many facilities of new and existing archival data to really look at the closest stellar and substellar companions. These were complemented with wide field plates. And so I used digitized photographic plates that span over 40 years between the first image in the 1950s all the way through the 1990s. And this allows us for a given star, at the example seen in the center of this image, to search for a binary companion all the way up to 10,000 AU. And the nice thing about our sort of backyard nearest neighbors is that they have massive proper motions on the sky. So here's an example. If we zoom in just to the center of this image and look at our star of interest, which is right here, you can see that in 1952, we have the star against a relatively constant background, but the proper motion of the star means that it's actually quite simple to rapidly identify binaries over the course of 40 years or so that are co-moving in space. So the results of this is that we found a sort of wide zoo of possible stellar companions. We see some really interesting hierarchical systems where you have 4 stars. We have systems for which a binary has been known for almost 100 years and the actual entire visual orbit has been determined. We found new companions that are sort of right at the stellar substellar boundary, and systems that are very widely separated, up to about 2,500 AU in separation. What you can do with this then is you can sort of look at the sensitivity of our survey and plot the mass of the companion. So how sensitive were we to actually being able to see a binary all the way down to the bottom of the hydrogen burning main sequence as a function of the separation of the binary with all of the systems overplotted. And this showed us that we had nearly uniform coverage and completeness, all over 95% complete to binaries down to about 3 AU in separation from the star. So I'm going to talk through these sort of busy plots just to sort of give you some framework for what we should understand about low mass stars. So this is just a histogram showing the fraction of systems as a function of the separation of the binary. And if we walk through each of these curves, we know that for A-type stars, when you find them in binary systems, the typical separation is about 300 AU. So the binaries are actually very, very wide. For solar type stars, FGK stars, it's a very broad distribution, but the peak is actually around 40 AU, which is interesting. That suggests that for the solar system, if the sun were to have a binary companion, it would likely be around the orbit of Pluto. Of course, we're a single star, but it's about a 50-50 fraction of sun-like stars with binaries. And then the previous results for M-dwarfs sort of were suggestive that the fraction was closer. And what we actually find from this study is that we actually don't see the histogram turnover. We don't see the distribution turnover. And so we see a lot of really, really close systems, but this is suggestive. The typical separation of these small M-dwarf stars are binaries that are only about 6 AU in separation. And that has really important implications for what you think might be happening for planetary systems. We know Jupiter is at 5 AU, we're at 1. Having a binary where Jupiter is probably going to have some dramatic impact on what's happening to your planetary system. So the takeaway idea here is that as you go to higher and higher mass host stars, the binaries become wider and wider. We can also just look at the frequency. How often do we even find a star with a companion, a binary star around it? And if you just focus on the sort of solid filled points here, the FGK or solar type stars come in at about 40% of systems that have companions, one or more companion stars. And then we were able to definitively show that M-dwarfs are significantly lower. So this is quite interesting in that as you go to lower and lower mass stars, the odds of being in a binary decrease. So that's maybe favorable if you're considering planetary systems, but the converse of that is that the binaries are closer. And you can see brown dwarfs, for comparison, are even less frequently found in binary systems. So I've been only talking about stars orbiting stars, but something that's quite interesting to consider are substellar candidates. So how often does an M-dwarf have a brown dwarf orbiting it? If we want to understand their planetary systems, we probably want to understand these intermediate objects as well. And so through the survey, we actually recovered Gliese 229, which was the first brown dwarf ever discovered in 1995, shown here in this image. And just for a bit of context, there was a recent paper this year that started to show that there might be something fundamentally different about how brown dwarfs orbiting stars form in a different mechanism than those of giant planets. And you can explore this looking at the eccentricity distribution, where giant planets tend to be on more circular orbits, but brown dwarfs show a very broad distribution of eccentricity that look a little bit more like stars. And so as brown dwarfs are sort of this intermediate, not quite star, not quite planet, this is giving us maybe some hint that the formation pathway of brown dwarfs is maybe a little bit more akin to stars. But we've been trying to explore this for M-dwarfs, and so I've had a team of students who have been working on analyzing hundreds of images where we have all of these, promising candidate companions, and trying to verify whether or not they are physically bound to the host star, and determine if we can get a handle on what the actual fraction of these systems is like. So in summary, for this first part of my talk, we know that the M-dwarfs that we see are not very often found in binaries, but they're very, very closely separated. We're trying to explore their substellar frequency, and something else that we can do that's quite exciting is that the binaries are close enough that we can trace out significant fractions of their orbits and start to determine the parameters of the distribution of orbits of these systems, and that will really give us some insight into formation mechanisms and comparison with things like star-forming regions. Okay, so I've been really focused on the sort of backyard 15 parsecs from the sun. I want to move just a little bit further away, of course, not nearly as far as I think what a lot of you are thinking about on a cosmological scale, but just 140 parsecs to the Taurus molecular cloud. So the Taurus molecular cloud, as you can sort of see in this image, is one of the nearest star-forming regions to the sun. It's really predominantly low-mass stars, so it has over 300 young stars and brown dwarfs. And it's only about 1 to 2 million years old. So it's a perfect environment to try and understand the properties of low mass stars and brown dwarfs at very early stages when their protoplanetary systems are quite young. So I'm going to talk a little bit about an ongoing effort called the Taurus Boundary of Stellar Substellar or TBOSS survey. This started with a far infrared census of protoplanetary disks around these objects with the Herschel Space Observatory. And so you can see some Herschel packed 70 micron maps showing significant dust excess indicating disks around these systems. This was a survey that was 150 objects that captured over 98% of the lowest mass stars and brown dwarfs in Taurus, and really focused on these kind of lowest mass objects, kind of like the TRAPPIST-1 analogs, these objects that are sort of right at the stellar brown dwarf boundary. We looked at a subsample of these objects way back in cycle 1 with ALMA, and we sort of looked at them across the entire extent of the Taurus star-forming region to understand sort of what their disk properties might be like. So the ALMA observations span sort of the stellar-substellar boundary. They had 10 times greater sensitivity with ALMA than any previous facility, and really allowed us to understand, looking at the SED here, what the submillimeter fluxes of these disks were like in order to understand how much mass exists in dust around these objects. And here you can see just a single map, a single extremely clean ALMA map, showing the beam size in the lower left, showing that we're not only measuring the dust, the amount of submillimeter size dust grains in these systems, but also spatially, starting to spatially resolve the sizes of these disks as well. So here's just a gallery of what we found by looking at these objects. We detected almost all of the M-dwarf disks. So this was exciting because it suggests that there's enough material essentially for planet formation at these early stages around these objects. And then what we weren't sure about is what we would find if we went to even lower masses to brown dwarfs. And we were pretty excited to actually detect all of the disks in our system. All of the brown dwarfs had ALMA detections, continuum detections. So we can sort of start to put this together to try and understand the demographics of the planet forming potential of low mass stars and brown dwarfs. So what we're looking at here is the mass of dust in these disks is in Earth masses. And this is a function of the mass of the host star. So the gray points are what we had measured in Taurus previously with pre-ALMA essentially. And I split this up into solar type FGK stars here on the right, the M-dwarfs, which span a pretty wide mass range, and then the brown dwarfs below the hydrogen burning limit. And all the red points are the points that we've added to this parameter space. So you can see there's this decline. So as you go to lower and lower mass objects, they have less dust in their disks, which maybe is unsurprising. But we wanted to sort of give a benchmark for this to understand how to contextualize this with the solar system. So if you take a very simplistic view of what's called the minimum mass solar nebula, so how much mass did the sun have in its protoplanetary disk to essentially produce Jupiter, which is the bulk of the mass in terms of planets in the solar system, you need about 30 Earth masses of dust and a 100-to-1 gas to dust ratio to form a Jupiter. And you can see that the FGK stars, the solar type stars, very comfortably fit into this regime, which is comforting because we have a Jupiter. But you can see that as you move to lower and lower mass stars, very few disks actually have enough mass to form a Jovian planet. Only the most massive M-dwarfs and essentially none of the brown dwarfs have sufficient mass to form Jupiters. And this is maybe telling us a little bit about what kind of planetary systems we should expect to find around the lowest mass stars. We can also look at the same axes of the plot in dust mass versus the mass of the star and compare as a function of age. So what we're looking at now is all in the black points are all of the objects in Taurus, all the 1 to 2 million year old systems. And then the teal points are an older star forming region, Upper Scorpius, which is roughly 5 to 10 million years. And although there's a huge spread at any given mass, you can see that there's actually a decline in the amount of dust by about a factor of 5. So this is giving us a really interesting handle on how quickly does dust evolve in these systems. And we can see that the dust is depleting, it's evolving, either forming into planets or being dispersed in some way over this 10 million year timescale, which gives us a window of time to potentially form planets. So in summary, this work has really started to extend the host mass-disk mass relationship into the brown dwarf regime for Taurus, giving us some sense of how dust depletes, potentially the conversion of small millimeter-sized grain into larger planetesimals. And the fact that we don't see that much dust around the lowest mass stars and brown dwarfs might actually help explain the fact that we have a really hard time detecting giant planets around low mass stars, and maybe the answer is they just can't really form them in the first place. Okay, so for the very last part of my talk, I'm going to move out a little bit and talk about just one single brown dwarf that's quite interesting. And I mentioned earlier that brown dwarfs, because they exist in this sort of intermediate space, are not just interesting to think about as planet hosts, but also as planet analogs. So I really like this visualization from Catherine Lauders that shows what happens in the atmospheres of these objects as you start from hot temperatures on the right. So an M-type star might have an atmosphere that's mostly CO gas. Maybe it has a few of these dusty metallic oxide species or materials like corundum. As you cool down to cooler and cooler temperatures, these clouds start to sink. You start to form different types of iron metal liquid. In fact, the hottest brown dwarfs we think have liquid iron rain that can condense out from the clouds and rain out in the atmosphere. As you go to cooler temperatures, your chemistry gets significantly more complex, and then you start to look a lot like Jupiter. So the atmospheric characterization of brown dwarfs is a really important stepping stone for us to be able to understand exoplanet atmospheres around lower mass, potentially someday even terrestrial planets. But the beauty of brown dwarfs is that they have much higher signal to noise than the imaged planets that have been discovered so much, and hundreds of objects to study and to form empirical libraries of these kinds of spectra. But there are a lot of questions, and part of the means to answer these questions was the motivation for the Gemini Planet Imager. So the Gemini Planet Imager, or GPI, is or was an extreme adaptive optics instrument on Gemini South, shown here in the little blue box on the bottom at the Cassegrain focus of Gemini South. The point of this instrument was to directly image and obtain spectra of Jupiter-type exoplanets at separations of 3 to 58 U. And we had a 900-hour survey to look at the nearest, youngest 600 stars to try and image their planets as well as their debris disks. And we discovered one in 2015, the lowest mass directly imaged planet to date, which is only about 2 Jupiter masses, its lowest estimate. It's shown here in this tiny blob with the size of Saturn's orbit plotted for scale and the central starlight blocked. And so this was sort of giving us some insight into the demographics of these systems, including a number of resolved disks and brown dwarfs as well. So this paper actually just came out about a week ago. Tom Esposito has shown the gallery of debris disks. So these are the remnant material, much older than the disks I was just talking about. But GPI has beautifully resolved, many of these ring and edge-on, even face-on disk systems that are essentially the signposts of planet formation, sort of the young analogs to our own Kuiper belt or asteroid belt. We also have a number of brown dwarf companions, as shown here. Some more orbit movies showing that we can actually, monitor the paths of these planets and see their trajectories in real time. And one of the beauties of using GPI is that GPI is an integral field spectrograph. And so the data products that we get are actually, an image that has 37,000 tiny spectra on it, which we then collapse, are able to process into a data cube where the central starlight is blocked, but we are able to see the spectrum of the planet through the data cube from the IFS. Just to give you an example of what this looks like, here's a video of Europa in the infrared, showing as you march through wavelength space, sort of what the brightness of the, well, not planet, I guess endoplanet looks like. And then here's a video of the atmosphere of 51 Aries. So this is the first exoplanet that was discovered from our survey. And you can see as you march through this data cube, you actually get a measurement of the spectrum of this object, sort of a very coarse spectrum of this object at various wavelengths. So why do we want to use directly imaged spectra instead of the spectra that we can measure through transits, for example? And this is just a gallery of what over 500 orbits of HST has produced for hot Jupiters. So for these transiting very close in hot exoplanet systems. And you can see that most of these are very featureless spectra. There's really not a lot of atmospheric features, molecular features in these objects. But if you go to direct imaging, you start to see a much more wide variety of atmospheric processes at play when you can measure the light from the planet directly. And so this is a really powerful tool to be able to measure the spectra, the emergent spectra of these objects. So I'm just going to talk about one object in particular. This is HD 206893. It's a very unusual brown dwarf. It's actually only the second brown dwarf that's ever been found orbiting within the debris disk of its host star. So you can see that the Herschel 70 micron image shows a significant infrared excess. If you zoom way in to this image with extreme adaptive optics facility on the VLT, you can actually see there's this very faint blob of light. It's only 0.25 arc seconds from the host star and was confirmed to be bound to the host star from its non-detection using Hubble. These are GPI images of the same object, and so something that you can see is just like those previous videos is that from 2016 to 2018, there's actually quite a bit of orbital motion in the companion in these different infrared bands. And then, as I mentioned, the beauty of GPI is that we actually measure a spectrum of the object. And so on the top here, I'm showing the flux as a function of wavelength in the near infrared, J, H, and K bands, and an L band point. And something that you can note just right off the bat is that the object gets significantly more luminous as you go to redder infrared wavelengths. And so this object is extraordinarily red. In fact, it's the reddest brown dwarf that's ever been discovered. Just to give you some context of what the spectrum should look like if you had a normal brown dwarf, down here is showing sort of the range of spectra for brown dwarfs of different colors of a L-type spectral type. And you can see, even in these cases, the bluer wavelengths, the J band is significantly brighter than the K band, but this object is, just a rapidly increasing mountain of flux. So we wanted to understand exactly why is the spectrum so red. There's some really interesting hypotheses for this. One of which is that we think that very red L-type brown dwarfs are likely to have a very small high-altitude submicron haze layer. And this, we know that this object exists inside a debris disk, so there's lots of dust in its native environment. One of the questions we have sort of posited is could this actually be a signature of an impact event? So we know that from Hubble observations of Jupiter, when the comet Schumacher-Levy 9 impacted it in 1994, that it left a lot of high-altitude particulate that was very, very small haze that made the object look quite a bit redder. And if you apply that treatment to this spectrum, you can actually reconcile this very red spectrum with that of a more normal brown dwarf of sort of intermediate temperature. And so we think that might actually be a possibility that it's redder from its debris disk environment in which it resides. The other thing that's really quite interesting that we can do, as I mentioned, is that we've been observing this object long enough to trace out parts of its orbit. So this is just a visualization of sort of the 250 best fit orbits to the system, to the movement that we've seen so far. And one of the things that we can start to explore is whether or not the object's orbit is coplanar with the debris disk, or if it's slightly inclined. And it looks like there's a little bit of a signature for some moderate inclination between the object and its debris disk. We also know that the object is only at about 10 AU in separation from the star, but the inner edge of the disk is 50 AU. So that's a lot of space where we don't think the planet is dynamically carving the interior of the ring, but there might be space for additional planets. So that gives us a lot of sort of looking forward to the near future and using these techniques on more M-dwarf systems. So as I mentioned, the TESS satellite launched 2 years ago. It has 2,000 candidates already, 52 confirmed planets. These systems will also be ripe for follow-up with James Webb, which will hopefully, fingers crossed, launch next year. And then also for what was called the W-FIRST telescope, which has been recently renamed the Nancy Grace Roman telescope, which will launch in the mid-2020s. And these will all be facilities which will give us insight into M-dwarfs and their planets, as well as the capability to directly image some of these systems, which will be quite exciting. And with that, actually, I will just leave you with my sort of summaries about the binary statistics, these objects' ability to form planets, and then what we can learn from characterization of these kinds of systems. And thank you for your time.
Thanks very much, Kim. Is there any questions for Kim?
So here I have a few questions. Okay, so first of all, very interesting talk. I am a cosmologist, so I mean, it has been a long time that I haven't heard any planet talks, and this is very interesting. Yeah. So my question may be a bit naive because I'm really working on the very other end of the universe. So the first thing is that I really want to understand the what you say called intermediate range. So I mean, as far as I understand, Jupiter might be the largest stable planet, and if the planet become even heavier, it should you know, become a star. So I wonder what is the absolute boundary demarcation between the planet and those objects which have could, you know, gravity can ignite nuclear fusion. So the stars. Yeah. What is the
Yeah, so what we found is that apparently there is nothing that astronomers love more than arguing about what makes a planet, as we've learned from Pluto, and the same is true for brown dwarfs. So there are a few different boundaries that sort of make sense. So the first one is at 80 Jupiter masses is the point where you can stably fuse hydrogen. So that demarcation between the hydrogen burning limit for brown dwarfs and stars seems quite clear. At the other end, at 13 times the mass of Jupiter, which is, you know, still quite large, but at 13 times the mass of Jupiter, you can stably fuse deuterium. And so people often invoke the deuterium burning limit as the demarcation between truly planetary mass objects and brown dwarfs. Now, that's a little, the reason that that's a little fraught is that that doesn't actually tell you anything about formation mechanism. So if you like to define planets as something, as an object that forms, you know, in a disk around a higher mass star, and that's how you define a planet, whether or not you can burn deuterium actually doesn't really factor into that, because we see what are so-called free-floating planets that are only a few Jupiter masses that don't appear to have a host star. And so it ends up being this sort of complex question of which formation pathway is really responsible. But just as sort of a handy estimate, the deuterium burning limit is often what people use to say brown dwarf.
Oh, okay, I see. Okay, very interesting. Yeah. The other thing is, yeah, just following what you explained, I wonder. So I look like there was a plot in your talk that look like there is like maybe 20 to 30% of the star which has these campaigning. I wonder what is their formation process. I mean, usually, I mean, I listened to several of these planetary formation talks, Doglin, etc. I mean, there was many different theory. I mean, one is something called fragmentation. So they have this cloud, and yeah, that is one thing. The other is some sort of a dynamic capture. So while they are, you know, moving around, and what could be the major formation mechanism? I mean, what is the fraction of different classes of formation scenario?
Yeah, it's a great question, and it's a really interesting, outstanding one, because for example, if you just think about higher mass stars, there's turbulent fragmentation, and then the sort of condensation of individual cores in sort of a star-forming filament of gas and dust. And both of those appear to be at play to form stellar binaries. Sort of an interesting question as you move to lower and lower masses is how efficient is that process, and does it still work that way? So we think that some of these M-dwarf binary systems are likely forming as sort of like core fragmentation processes in the molecular cloud, where cores based on sort of turbulent length scales within the molecular cloud, can fragment on very small scales and allow you to form, close stellar binaries. There's actually sort of a sort of additional question for brown dwarfs, is that we're not clear if brown dwarfs form through that channel or if they form sort of from the ground up from disks around objects. So I think there's a possibility that multiple formation channels are at play, but we think that a lot of the sort of standard core formation arguments for star forming regions seem to work for M-dwarfs at least.
Okay, and then another one is you mentioned about the adaptive optics. So I also saw this kind of thing in the strong lensing study, which they try to correct for images for the for the lens, and so therefore they get better estimate of the delay, time delay, etc. So I wonder, I know this system can only apply for small angular systems. So I wonder what is the limit of that AO technique? What is how large the AO can treat? Mm-hmm.
Yeah, so like on a spatial scale, like an arc
Yeah.
So one of the things for extreme adaptive optics, which is like the JUPI instrument, for example, our field of view is only an arc second on a side, and that's very limited because we care about those separations from the host star. But it's also a sort of a question of contrast, like what is the faintest sensitivity that we can get to at the very closest angular resolution. Something that's quite exciting about AO, though, is that people have been pushing the technique to cover wider fields of view so that you can get the same correction and the same resolution, but instead over like arc minutes fields of view. So those are coming into place with like kind of different sophisticated AO systems on the VLT and LBT telescopes that allow you to have the same kind of correction and not quite the same sensitivity, but much deeper sensitivity over larger fields of view, which are really great for things like surveying extragalactic galaxy groups, galaxy clusters. Whereas the AO that I've talked about today is probably really sort of on an extragalactic scale most exciting for things like AGN hosts, if you care about the really high angular resolution environments of epicenters of galaxies. So anyone has interest in that, we are always trying to get extragalactic astronomers interested in extreme AO. What can we do with this contrast and sensitivity for extragalactic science as well?
Sure. Yeah. Oh, thanks for answering. Thank you. Yeah.
Any questions from other audience?
Yeah, I had a question about the spectra. So if I understood correctly, you were saying or also showing that the spectra that you get from the transit are rather bland and featureless, whereas the directly imaged ones, you could see sort of lines and stuff. And why should they be different? It would sort of seem that it would be the same technique, different techniques to get the same spectrum.
Right. Yeah, that's a great question. I think it's something we're still wrestling with a little bit because when the first transiting exoplanet spectra were taken, people expected to see more robust molecular features, more signatures of, water, methane, et cetera. And we're sort of surprised to see all of these flat featureless spectra over and over again. So right now, we think the reason for that is actually sort of which parts of the atmosphere we're probing with the different methods. So the transiting spectra we get right now require the starlight to pass through the planet's atmosphere as the planet eclipses us, or we see the signature of the planet disappear as the planet passes behind the star. So there's two ways of doing that. But that might be sort of probing a slightly different astrophysical component of the atmosphere, as opposed to sort of like peering straight down into the atmosphere, looking through a different column density of material. So part of it we think might be like, we might just be seeing hazes or things that prevent us from seeing more interesting atmospheric features in the transiting systems just because of our viewing geometry. Part of it might be the actual chemical makeup of the atmosphere itself. And then part of it might be the actual ability to probe the atmosphere sort of directly or indirectly.
Oh, so in the transit, a lot of it, you're saying just comes from the edge, the starlight going through, and
Yeah.
it's more like an absorption spectrum than if you would put the planet aside.
Exactly, yes. And then there's all kinds of systematics in trying to deblend the starlight contribution from that and make sure you're only getting the planet signal as well. But yes, that's generally the idea that you're basically seeing it. You're seeing the starlight through the like peripheral lens of the planet atmosphere.
I see, thanks. That makes a lot of sense.
Any other questions? Matt?
I had a question. Back on the atmospheres again, but the directly imaged ones, how much information can you get out of those spectra? Like they look quite low resolution. So what can you actually?
Yeah, we get teased a
Let
little.
me, yeah, I have similar question too. I was wondering if you were able to distinguish any metal component from that spectra, and does it fit with what you were hypotheses in the atmospherics modeling?
Yeah, that's a great question. I wonder if I have, oh darn, I don't have I was hoping I had a backup slide to address this, but yeah, so I guess the first part to Matt's question is, so we get teased a little bit with GPI that we call this a spectrum because our resolving power is like R of 37, right? So it's not like a stellar spectrum, even moderate resolution spectroscopy. But that said, the features in these exoplanet spectra are very sensitive to things like surface gravity, the temperature of the object. We get some handle on metallicity as well, because small changes in these temperature regimes, small changes in those properties actually manifest as pretty large-scale morphological features in the spectrum. So even though we're only operating at R of a very small number, we can still see things like surface gravity makes parts of the spectrum appear sharper or broader, or the different absorptions of things like water in the atmosphere at 1.4 microns. So basically, sort of to get to Boom's question, what we end up doing is we take these atmospheric grids of models that vary in effective temperature, surface gravity, and composition. And then we basically just test these spectra against them to try and derive the parameters. And usually we can get to an effective temperature within a couple hundred Kelvin. We can try to estimate the radius of the object from this method. Metallicity is a little bit harder just because there's not a lot of extremely distinct features, but we do get some of the handle of the different physical characteristics. Yeah. And ideally it will only get better as we're able to do the same kind of AO with higher spectral resolution in the future.